Okay, welcome AP Chem students to your second instructional video. This video is going to focus on what is a physical property, what is a chemical property. In chemistry, it is utmost important to understand the difference between a physical property, a physical characteristic, a chemical property, a chemical change. Is it a physical issue? Is it a chemical issue? Often asked back and forth. So even though you may think it's obvious, you have to sometimes stop and look at the context. What are the words saying? Am I looking at an immediate thing that's happening, or is it something that happens after I mix two things? You have to keep asking a lot of questions about what is the context I'm reading and how does it imply I performed in the lab or in the classroom or whatever I'm doing. Okay, so a physical property has to do with the physicality of the material, why we call it physical. Right, so it's something that you either observe or you can measure. And here's the key: anything physical will happen without changing a substance composition or its identity. You can get it back. By physical means, not chemical, right? So physical means meaning filtration, chromatography, physically separating by a magnet or tweezers or a sieve, right? That's what I mean by physical means. Evaporating the water, changing your phase, right? Did you move from a solid to a liquid to a gas? It's all the same material, but you're changing its physical appearance, okay? So there are two types, right? Type 1 is what we call extensive, which depends on how much is present. Type 2 is intensive, doesn't depend on how much is present. It's almost like a constant value. Okay, now this is where it gets tricky because one intensive property is color. But you have to be careful because this type of color is the description of the material. The crystal is red. Now, it doesn't matter whether you have a pile of crystal or a single crystal. It would be red. The intensity might be greater with a pile, but it's still the same color red. Okay? It exists as a color. So one thing here is you have to be careful because, and I'll put a little asterisk, because color can be a physical description, but color can also result from a chemical reaction. So in this case, color is intensive, but you have to be careful how color is used in context when they ask a question. So things that make sense in terms of extensive depends on how much. Well, volume's one, mass is another, right? If I have a big mound of it versus just a tiny itty bit of it, you're going to have a different mass. Same thing with the volume. If I got a lot of stuff versus just a little bit of it, you're going to have a different volume. Right? So understand too that volume, which can be measured different ways, we can measure it by water displacement. We can measure it by actual, graduated cylinder. Okay? If you're doing a solid, you can measure it by length times width times height, all extensive properties. If you can't physically measure the material, this is an odd shape, let's say it's a rock, you can do it by putting in water and looking at how much volume it displaces. If you have a liquid, you would measure it by a graduated cylinder. Okay, you pour it in and you take a volume measurement. You can measure it also by a burette if it's a liquid. You can measure it by a volumetric cylinder, which measures a very precise and very accurate amount of material. Okay, accurate within plus or minus 0.0001 milliliters. It's milled that way. It's made that way. Okay, so that's volume. Same thing with mass. Your accuracy of your mass will depend on how many digits your balance can go out to, how sensitive it is, how much degree of significance is in your measurement. But there is one physical property that we measure, and you spend a lot of time on this in 7th and 8th grade, called density. Density actually is intensive, which is weird because mass is an extensive characteristic. Volume is an extensive characteristic. Sometimes AP, to test your physical knowledge, will ask you about what about density? But density itself, if mass goes up, volume will go up, and they'll go up proportionally so that this will always stay constant. A material's density at a set temp will stay the same as long as you don't, and I'm sorry this keeps making lines across the video, guys, but it's the best I can do right now. So it'll be constant at a set temp. It will not change. You change the temperature, you're going to change the density. But if the temperature remains constant, that material's density remains constant. So like aluminum is 2.70 grams per cubic centimeter at 25 degrees Celsius. Okay, that is a set property. Okay, now switching gears, going to a chemical property, looking at the word, we are going to deal with things in chemistry. The type of reaction it can do, its potential to do a reaction. Does it react with something? Does it cause a change? Right, so it is undergoing a chemical reaction and you get a change. There is a change that takes place. All right, I often say to people, can you get the starting material back? If you want to say, is it physical or is it chemical? Ask, can you get the starting material back? Can you go backwards? Right? So, ice to water. Yes, I can get that back. I can go back to ice again. These are all physical changes. But if I have egg, flour, sugar, let's use milk, and I make a cake, right? Can I go backwards and get all of that back again? And if the answer is no, then I've done a chemical change. I can't get it back. And you have to understand, I can't go backwards physically. Right? I'm going to really stress that. Physically. Oh, you can't see the ALY over there. So, in other words, this is not balanced. I'll balance it. It'll bug me if I don't balance it. I make water. This is new compared to this. This formula over here is not the same as the two formulas there. Can I go backwards? Yes, but not physically. In order to go this way, I have to do a chemical decomposition. So both directions are a chemical change. Right? This here, I didn't have to do anything except raise or lower the temperature. I didn't change it chemically. It's still identified as a form of water. I changed its ID going this way. I changed its ID going that way. That's a chemical change. Okay, so what do we look for? These are signs of a chemical change. Right? They're not saying it absolutely is, but it's a sign. Change in temperature, not meaning we added temperature. In other words, mix two things together, it gets cold. Okay, that's a chemical change. Change in color. Mix two things together, you create a color. Or absence. The color goes away, clears up. You produce a gas. It can smell or it could just bubble. You produce a solid. In other words, I take a nice test tube with a beautiful red solution, and then I take a next test tube and I'll change the color on this. Let's say the solution is blue, right? And I pour them together into a beaker, and what I get is, it's not going to look that way. Since you have a white, I don't have a white. I get a clear solution, but on the bottom, I get like yellow precipitate. I had a solid on the bottom. This, all the color goes away, but then I got this chunky colored solid on the bottom. Right, that's a precipitate. One of the terms you're going to hear often, we are going to talk about this so often, is this thing called a precipitate, a PPT. Right? PPT means you are making something solid. So the reason why they call it a precipitate is when you visually watch the reaction, you pour two things into a beaker, they start to mix, and over time you see little crystals fall to the ground or fall to the bottom of the beaker. We're going to do this, hopefully, or I'll just demo it for you. So they fall to the bottom of the beaker. When they fall to the bottom of the beaker, it's like snow falling, and we call snow as a form of precipitation. So when you make these little things fall, crystals fall to the bottom of the beaker, it is precipitating. Okay, so to sum it up, to get a physical change, you're going to change something that doesn't alter the composition of the material. You can get it back. Okay, the big thing on that is phase changes, guys. A chemical change will be a compositional change. It's something new. And you can't get the original back by physical means. I can't take a tweezer and pull it out. I can't condense it. I can't, evaporate it, whatever. It has to be chemically separated. This is a big one. Phase change is physical. pH, phase physical, phase physical, phase physical. Okay? People make a mistake. My APs did it when they took the exam, rushed for time. They were telling me a phase change when they took the AP exam was a chemical change. It's not. Phase physical. Okay, phase physical. If you dissolve AQ, any dissolving, because there are other solutions besides AQ, but anything that's AQ, you can get it back by evaporation. That is not chemical, it's physical. Right? So keep that in mind. I can't stress this enough. I can't tell you throughout the year how many people will forget that phase is physical. And all I can say is phase, physical. I know you're like, oh my God, that's so frustrating. But I'm telling you, I can't, that probably 50% of the kids got it wrong on the AP exam last year. Right. Chemical change. Keywords. It reacted. Keywords. It burned. It oxidized. Oxidize is another word for rust. It produced. It yielded. It created. Okay. Burn is very specific. Burn means combustion. Okay, when we use our Bunsen burners, that is combustion. All right, let's see. Oh, measuring. All right, measuring is a big thing. Take a moment, pause the video, fill in everything. Once you've got it filled in, start the video again, and I'll explain the units. So right now, pause and fill in the 2 boxes. Welcome back from pausing. If you didn't pause, pause and fill in the boxes. So now, units are critical. For AP, you need to know units. Some of the units are given in your reference sheet you're going to get. I can show you where to obtain that. I'm going to post the curriculum up in our Google Classroom. And unfortunately, you have to go like all the way to the end of that curriculum before you can pull out the reference table, right? If you get stuck. What I'll try to do, guys, is also scan it in and post it up just as a scanned material and say, okay, here's your ref table. Mass technically is measured in kilograms for what we call the international system. SI means the international system. Comes from France, so it's French Système International. So a bunch of pure and applied chemists. It's called IUPAC, International Union of Pure and Applied Chemists. Okay, that's pure and applied chemists. IUPAC. Whenever you see IUPAC, don't panic. It just means name it the way you're supposed to name it. Use a unit the way you're supposed to use it. It's not a big deal. In our lab, our base unit is grams. And now I'll tell you what I mean. This is a base unit right here when we go to convert prefixes. So mass is grams in the lab, and then the international unit is kilograms. Like how much do you weigh, which is really your mass. It's kilograms. Length is meter. Meter is also a base unit. So we have the meter stick, and then we have so many kilometers, or we have so many millimeters, or we have so many nano. That's the big buzzword. Nano, 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 nano. Okay. Then you have time, always measured in seconds. Could it be something else? Yes, but the international unit is seconds when we talk about chemistry. Temperature's actually international unit is Kelvin. We will start with Celsius to begin, and then we will be working completely in Kelvin as we get later on in the year. We will talk about electric current. You'll use that more in physics, but it's an ampere. But we will talk about it when we do redox, because we will make a battery and we will power, and hopefully by then there will be treatments and vaccines for COVID, so we can really do labs. We will talk about this whole unit. This is a special unit called a mole, and that is also a base unit. Like down here we've got liters, meters, grams. You can also have down in moles, because you can do millimoles and you can do megamoles, believe it or not. And no, it doesn't have to do with Austin power. Luminosity is measured in what's called a candela, like how many candle lights, candelas, but we don't use that very much. And we have, a lot of times now they call them lumens, if you look at light bulbs. Pressure is pascals, but we will also use ATMs for atmospheres. And I will add the time when we go through this, because this is to go back and forth between this. It's really kilopascals that we use. Pascals and ATMs get converted back and forth. We will learn about millimeters mercury, and we'll learn about torrs, because Torricelli was the one who developed a way to measure pressure. And I'm missing one. Oh, yeah, PSI, but we don't work with PSI. That's too English. Okay, now, this must be memorized. You will not get that in AP. You need to know it. You need to know how to do conversions. I will show you a couple different ways to do conversions, but we are going to focus on what is called, a couple different things. Dimensional analysis, so I call it DA. Some people call it the factor label method. And I have to tell you, Mr. Strace makes you do this, but so did my physics teacher way back. 40 years ago for me in high school. Always had to put units in first and make sure they canceled. And you got the unit you needed for your answer. That's a factor label method. In physics, to check to make sure you're thinking correctly and you're substituting incorrectly, you always put the units in before any numbers and make sure you get the units you want. And you need to know how to convert between units, because a lot of times they'll give you something in millimeters and your end measurement has to be in kilometers. And you have to be able to convert whatever you have, do your math, and then convert it. So it's very important to be able to do either what's called dimensional analysis, DA, or FLM, factor label method, right? So technically, when you use dimensional analysis, you're going to start with something that's given and you're going to multiply it by the conversion unit. Okay, you have to remember what's your base. This is getting annoying. And it's funny, don't laugh. I took my computer in because it was having issues where I'd get announcements about, oh, your virus software is out of date. And I knew it wasn't because of what we use, but IT said, oh, bring it in because we want to check it out and we'll update it. Yeah, they update it and now I have problems writing on the screen. It always happens. Okay, so you start with a given unit in the problem. So this is your given. And then you're going to multiply it by what you want on the top. So this is going to be the desired unit, what you're trying to get to. And then what's its conversion from the unit given. So if I have, there is 10 to the minus 3 meters for 1 millimeter. Then if I had 1,000 millimeters and I wanted to go to meters, I would say, oh, and usually, and I'm actually doing this the wrong way. Let me start that one over. See, even when I go to explain, I had to make sure I'm explaining it so it's easy for you. You're probably like, I just wrote all of it down. Don't worry. So get rid of that silly line. Let's go back so I can show you what I mean. Whoa, come back here. If I'm in meters, 1 meter, okay, 1 millimeter is 10 to the minus 3 meters. Didn't have it right. So if I'm going to go between millimeters and meters, I'm using 1 meter. I'm pen challenged today. 1 millimeter is 10 to the minus 3 meters. Yeah, that's what that means if you have a millimeter, the exponent up here is -3 in terms of meters. So milli is 10 to the minus 3. So if I'm going to go, and I'm using easy values here, 1,000 millimeters to meters, and I do my dimensional analysis, I would set it up. Here's my given. My factor, because I want to cancel out the millimeters, and I want to get to meters, I set it up with meters on the top, millimeters on the bottom. According to the chart, 1 millimeter is 10 to the minus 3 meters. Okay. Now, mathematically, guys, you should be able to do this in your head. You should be able to convert this to 1 times 10 to the 3. That's 10 to the minus 3. When you're multiplying, you add these together. So my answer would be 1 meter. If I had 0.082 meters and I wanted to go to millimeters, I would set up my conversion. 0.082 meters. I'm going to cancel out meters, so millimeters go here, meters go here. On the previous page, 1 millimeter is 10 to the minus 3 meters. Again, I can change this to scientific notation. And if I am dividing, I can just look at this value and this value. When I divide, I subtract. So minus 2 minus a minus 3 gives me 1. So now I will be 8.2 times 10 to the 1 millimeters, which is the same thing as 82 millimeters. No calculator necessary. We are in powers of 10. Here comes trickiness. Right, I'm going to erase my text so you can see what's written there. And you're probably like, I didn't know where to write that. And that's why I tell you, have a separate book. So if you want to make annotations, you can make annotations. You can write it in the margins. You know, you have to start learning how to fill in your own notes and make them make sense to you. Okay. So again, oops, it's my temperature thing. Let me go back. Let's do a more difficult one. Let's go kilometers to, let's say, nanometers. Right, so we're going to have a huge number for our nanometers. I have 70 kilometers. And I want to go to some, like, how many nanometers is that? Well, on the previous slide, right, 1 kilometer is 10 to the 3 meters. 1 nanometer is 10 to the minus 9th meters. I'm going to set up my dimensional analysis. 70 kilometers. I want to go first to meters because I'm going to go through my central unit, my core base unit. Whoops, sorry, that's 10 to the 3. Whew, that looks messy. I always will tell you I'm technology challenged. I try to do the best I can. And now I need to go to nanometers. Nanometers. And this is going to be meters. 1 nanometer is 10 to the minus 9 meters. Now again, I'm going to subtract. This is 7 times 10 to the 1. Right? I'm got 7 times 10 to the minus 10 to the 1 times 10 to the 3 is 10 to the 4th. Add them. 1, 4. Right? And then I'm dividing by 10 to the minus 9, which means I do 4 minus a minus 9, which will give me 13. So right now I have 7 times 10 to the 13th. My answer is 7 really 0.0 times 10 to the 13th. Well, actually, no, you can leave it 7 because I didn't put a little dot here, and we'll talk about that in next topic. Okay. Temperature scale, there's conversion. We really won't convert that till later. And we will hold off right there. That is our second lesson.